The presentation title follows: Quasiperiodic behavior of parametrically and physically forced pendulums with one and more degrees of freedom. Presenters Paweł Olejnik and Jan Awrecewicz from Lodz University of Technology and Michał Fečkan from Comenius University of Bratislava. Scope of the presentation. First of all, problem description will be given. A parametrically and physically excited oscillator subject to the periodic and almost periodic step and free change of the length will be presented and solved analytically and numerically. It will be shown that the nonlinear dynamical systems A with periodically modulated length, B springly attached to the force weakly damped slider, will synchronize with the forcing, manifesting a quasi-periodic behavior on a stable limit cycles. And finally, numerical computations and analysis will be done to confirm correctness of the analytical derivations and the models. We will end with the conclusions. The two types of parametric forcing. The pendulum model is considered in two mathematical problems. The first problem is associated with the periodically modulated length, and the second problem, in the second part of the presentation, is associated with the dynamically varying length. Equation of motion to the first problem. So we consider the damped mathematical pendulum with functionally changing length Ln, and it will be a discrete value here, in the equation 1, which describes motion of the pendulum with a sudden almost periodic change of length together with an external force at Tn. This force is defined as below. So moreover we suppose the following conditions, for instance, for t in each time interval between Tn and Tn plus 1. There are some limits and boundary assumptions and some constants, like for instance omega 1, omega 2 and omega 3, visible for instance here, here and here. So Ln is our modulated length, which takes a form of a discrete step wave function. The time t in the interval Tn plus 1 will change according to this formula, where S belongs to the interval 0, 1. Putting t to equation 1, we find two first-order differential equations, like these ones here, with the following initial conditions. Constants of the model are given here. We solved the numerical problem of an externally excited damped pendulum with a jumping length, and we have to make some conditioning of the problem. By defining the two step functions of modulation of length and forcing, where forcing is not visible here, here is Hn shown, which shows a variation of step of integration. Duration of time intervals on which the solution is computed changes as well. According to that, we take into consideration obtaining of a piecewise continuous solution according to these steps, on each of the intervals satisfying the initial and final conditions superposed on phi and phi dot. And as it is shown here, for two exemplary realizations, the pendulum length will change 8 times or 16 times, as well as in these intervals the time step will vary 4 times and 12 times. On this slide we see the first attempt to the numerical solution of the problem. A piecewise continuous time trajectories of the two states phi and phi dot are shown in a very initial stage at the time instances Tn I, where I goes over each time interval on the time horizon from 0 to 19. We see that the model starts from 0 initial conditions and quite fast synchronizes with the external forcing. Here we see a much frequent modulation of length Ln, I mean about this case. And it is again a step wave function of modulation of the pendulum length and corresponding step of numerical integration Hn. So smaller values here, omega 1 and omega 2, provide a much smoother form of the excitation. The solution can be now shown on the phase plane phi and phi dot, and it can be seen that the continuous limit cycle trajectories are constituted on the phase plane in a very long time period where the transitory stage of solution was omitted to check if the solution is stable. So 1000 initial time intervals has been rejected to omit any transitory behavior of our dynamical system. It has turned out that the limit cycle solution shown in this figure does not change, so we took it as the stable quasi-periodic trajectory. The synchronization of the obtained limit cycle solutions with external excitation is again visible. So the number of the periods here will cover with the number of excitation periods. And the much frequent solution presents again a stable limit cycle, and it proves again existence of an almost periodic solution on which the Poincare map should be closed, should show a closed curve. Worth noticing is very small, are the very small omega 1 and omega 2 for the excitation, and also a very small parameter of the forcing En. And now we are switching to the second problem, which is associated with the dynamically varying length of a pendulum attached to a sliding body. Description of the second problem. We have a slider and a pendulum which is attached to its center of mass. The pendulum length varies along S direction and has point focus mass m. The pendulum rotation is measured by theta. Displacement of the slider is xt. Pendulum. Next slides present derivation of equations where the kinetic energy depended on angle of rotation, elongation, and translation of the slider, and its derivatives respectively are used. Potential energy is also derived for the system. It is dependent according to this formula, which can be transferred to this one with the use of geometric formulas. We apply Euler-Lagrange equations to find equations of motion of the model. So for each component of the vector of general coordinates yk at independence of the assumed general coordinates, the Lagrangian L constructed from the previous functions satisfies the following form. The only term not known here is the dissipation term. This term can be calculated with the use of the Rayleigh dissipation function of this form, where according to our assumptions the viscous damping of motion is associated only with the pendulum body operating in S direction. Collecting all the previous derivations together, we find a system of 3 second-order differential equations, where each of them describes dynamics in the corresponding dimension, theta, s, elongation of the pendulum, and translation of the slider. It is interesting that translation of the slider could be extracted from the description, and for instance, it is present here and here. Observing that, we can reduce the model and its form. Derivation at the first attempt to the problem was considered in the work published in Latin American Journal of Solid and Structures. And the numerical solutions. Here we can see phase planes, the grain lines, and Poincaré maps, blue, green, and red, for the case of weakly damped variable length spring pendulum. For instance, Y2 is elongation of the pendulum and its Poincaré map. These Poincaré maps are present closed curves composed of points, of course, so it is obvious that they are scatter graphs, but when observing it long enough, then we can find closed curves, proving that the almost periodicity is found. Supplementing this description, please take a note that the observation was very long, as well as a very long transitory period of time was omitted to find them and to prove that it is stable in long-term observation. And we arrived at the conclusions. from which the second one sounds. There has been shown existence of almost periodic solutions manifested by both dynamical systems of various complexity that synchronize with the parametric, functional, and dynamical forcing. Thank you very much for your attention.